Hello everyone. We are the Smart Lawnmower team. My name is Alberto Moreno. My partners Jose Piñon and Rafael Jimenez. So the design objective is to design an automatic lawnmower, which is going to be controlled by a microprocessor, powered by a rechargeable battery. That's going to be able to mow a rectangular area for about 30 minutes. And the project principle is to facilitate people that cannot complete this task and reduce the time of mowing the lawn for oneself. Also for our principals to gain knowledge on microprocessors. So there's going to be 3 stages for the design. One's going to be the electrical, the mechanical, and the controlling system. Also, here's the Mow Pattern that we chose for the machine to mow. It's going to start at a certain corner of the rectangular area and finish at the center. So for the electric system objective, mainly is to support to supply power to all the electric components, determine the specific motors that we're going to be using, and to assist on the programming. Here's my initial Gantt chart, and my final Gantt chart, which I added this couple of weeks ago. We've been testing, and with the code we had some problems, but we let it work. So the design components, it's one 24 volts citric acid battery, one 12 volt citric acid battery. It's going to be 2 switches, safety switch, the step down converter from 12 to 5 volts, 1 motor driver, 2 DC wheel motors, 1 Arduino microprocessor, the IMU sensor, which has accelerometer, speedometer, and gyroscope, 1 GPS, and cables and connectors. In my part, my budget plan was for about $22, and I could get it to $189. And the main motor for the cutting mowing is just simply from the battery to switch to the blade motor. And the general view of the electric circuit, it's the 12 volt DC battery to the switch to a fuse. Then from the fuse goes to the motor driver, and also to the step down converter in order to convert to 5 volts for the Arduino. From the GPS sensor and the IMU sensor, we send the data to the Arduino. Then the Arduino does the magic, sends the signals to the motor driver, and the motor driver to the wheels, to the motor wheels. So our motor wheels the brand is Micro Motor. They're 12 volt DC volts. It has high torque, 11.5 Newton meters, and rated at 50 revolutions per minute. On our driver, it's rated from 5 volts to 36 volts to work in any range, and rated at 15 amps. So basically, we just have to do the connections to the 2 motors right here, and ground and power. And the other side of the motor driver, from the signals from the Arduino. So it's basically the PWM for one motor and the direction of one motor and the second motor. And these are some of the results, which in here is a plastic compartment where all the components, which I feel previously, they're in here, so we can protect for any garbage or water or something. It's already protected. The battery and the motors. And the result of the machine, once we test it, the average speed is 20.28 meters per second, which is about 1 kilometer per hour. We tested it on a flat surface, which is 7.6 meters by 7.6 meters. And the machine weight was about 25 kilograms.
For the mechanical system, there were two main objectives that I have to go with. First, that I have to install two-wheel. Well, at first, that was from last semester. At first, we were planning to install two wheelchair motors and also get a swivel kit which are from those type of wheels which let the wheel rotate 360, and this way will just follow the movement of the machine. Some of the constraints are to get the traction or control the machine, because sometimes to make a turn, or it will be sliding the tires. Also to make the front wheels to follow the movement of the machine. First I did some research. There was this prototype which had some wheelchair motors, and then they connected the wheelchair motors to the back tires using a chain and some gears. And also they were using that swivel kit, which is those type of front tires that rotate 360. And from there, I started doing my design. This was the machine that we got. We chose this machine because it was cost efficient. Also, it had all the requirements that we needed, which was electric and cordless. And on the right, the first modification was to put a plate on the back and to place the motors. And from there, I was planning to connect them using some gears. On the side, I was going to put that hole because the outlet for the trash for the mower was going through the back, because it was first a back, it was there in the back. So I had to do a hole in the side. And on the right, you can see the front wheels, the front tires, which let the mower to rotate freely the 360. And from there, when we started getting the parts for the installation, I choose plywood plate to put on the back for the support of the motors, because it was cost efficient, and also there were some on the machine shop. And from there, I had to do some shaft extensions to connect the motors to the wheels, because there were different sizes of the shaft for the motors. And also I put I think it's called a point screw, so it can fix the motion of the motor to the shaft and then to the tire. From there, there was this installation of the motors, which also all that material was on the machine shop. And also from there, we changed from wheelchair motors to 12 DC motors. For the front tires, these were built in the shop. Also, which was, this part was from another type of swivel kit, and then we adapted to our machine using a threaded rod And by the time we started there, we used some washers and nuts from top and the bottom, and just to fix the front tires. After the first test, the 4 tires were the same size, which were 5 inches in diameter, but that didn't help the mower to get the traction needed to make turns. So we opted to upgrade the tires and get some bigger tires. And also I had to do another shaft adapter for the tires. And for the front, for the front end, because it is plastic, it was getting off level. So we opted also, Quentin gave me the idea to put some coils so it can act as a suspension and lift the front of the machine. So the front tires were level and were able to rotate 360. After the second test, we opted to, one of the tires was touching the machine, so we opted to, instead of 2, just put one tire in the front. And also I had to find a place to put the second battery, which was for the motor, so we put it on the back, so this way the weight will be balanced, and also there will not be that much of a stress in the front wheel. And for the Gantt chart, there were some changes because we had a delay on the motors, and also the testing wasn't until that last week, so there were some changes with that.
For the controlling part, my name is Jorge. The controlling objective is to design the controlling system that's going to make the device move the rectangular mount automatically.
Do you know?
Actually, I add
If you don't know,
that we can control it with a cell phone application. This is the general view of the controlling system. Basically, we're going to have to control the 2 motors for the movement. I'm going to be using the motor driver for that, and that's going to be the output of my controller. For the inputs, I'm going to be having an IMU sensor that's for heading, a GPS module that's for positioning, and a Bluetooth module that is going to be for communicating with the cell phone. For the microcontroller board, it's the actual components that I'm using. I use most of the cost-effective components, and for that doing board, I was at first using the PIC microcontroller. The first senior design, I developed the code from scratch to read the values from the sensors, from the gyroscope, for the IMU and for the GPS, and also for control the motors by PWM. But I have trouble when I was trying to put all the code together, so I asked Jose and Luis for help, and they said they will help me better with the Arduino board. And what I have done with the PIC microcontroller in months, they did it in 1 to 2 days. So I changed it to the Arduino board. Basically, I choose the PIC microcontroller because I wanted to learn how to control. And for the components, the inputs, I use the Bluetooth, as I said, for communicating with a cell phone. It's an application that I made in the MIT App Inventor. And this application is controlling for going forward, going moving forward, backward, and turning left or right, and to set the positions. And the IMU, the other sensor that I'm using, this is, as I say, for heading. This sensor contains the gyroscope, the accelerometer, and the magnometer. That is a compass. I'm using the magnometer reading that gives me the heading of the machine. But this has some errors, so I have to combine the accelerometer and the gyroscope for field compensation. And I found some people that have made the field compensation on the internet. So I just made what they do. For the GPS module, you can see this one wants to, it's going to be used for set the boundaries of the rectangular now and for positioning the mower. So here we can see the latitude, this GPS gives us the latitude and longitude. And as we are in the second quadrant, that's the northwest quadrant. So I don't have, my code was easier because I don't have to worry about negative values or positive values. So I get the initial positioning to set my boundaries of the rectangular one. And it's going to be the position 1, that one corner, position 2, position 3, position 4. But in order to develop the algorithm, the moving algorithm, I found that the easiest way for me was to calculate the distance between those points. Here is the turning algorithm that I developed. This is the formulas that I was. Okay, I looked for the rectangular mower, and there's those squares. The length is the diameter of the blade. So I developed this algorithm that in the first loop, what's going to be the equation related to the initial value, initial distance that I did first. And at the end, it's going to be mowing that way, and it's going to stop when the distances are less or equal to 0. For controlling the wheel motors, I have to control the motors to adjust the heading and to turn 90 degrees to change the direction. So I use the motor driver, and the motor driver has 2 inputs. Basically, that's the tire is for the direction, and PWM that controls the speed. For the direction, it's very easy. We have the high or low, depending on how you connect the motor. It's gonna turn in clockwise or counterclockwise. For the speed, I use the PWM. It's the pulse width modulation, and basically it's I control the speed based on the Dury ratio, and the Dury ratio is the time the signal is on over the period of the signal times the 100%. For turning 90 degrees, this is for changing direction. For turning left, for example, the left motor is going to be moving backwards, and the left motor is going to be moving forward, so that the rotating point is going to be in the middle of the motor. And this gives more curvature, so you can turn easily to 90 degrees. And for adjusting the heading, basically I change the rotating point on the left or the right depending on the tuning. I have to just keep moving, but increase once the speed of one more to adjust the heading. And this, then my logic of mowing straightly is with the angle, and if it's more or less, control the motor. And that's it for my expenses. I spent $38. It's my bank account that I had to adjust it for when we were expecting the motors. And the results, I just get the error of minus 5 degrees on the IMU sensor when it's tilted, and error on GPS plus minus 1 meter. But we made one test, and we just we tried to calibrate the sensor, so we get 1 plus minus 1 feet. That's plus minus 1.3 meter. That's less than the diameter of the blade. This is the video for best. We're trying to make the device more straight to the line, to the white line.
That video took about 2.5 minutes, so we have to fast forward for time purposes. But it's on YouTube if you want to watch it. What's the name of UTRGB lawn mowers? I'm kidding.
Are you programming to make it move now, or you are controlling?
We're programming the GPS. Based on the code, I tried to set the error less than what was I had. That was 1 meter. I tried to reduce it to the 1 feet, and
So what is the current resolution about your GPS sensor now? So 1 meter or?
1 meter. Just in this test, because the GPS changes, they can change depending on if you turn it on and turn it off and turn it on again, it changes the position or the error, or where it's gonna be having the error. Maybe the error is gonna be in this and on the right, maybe on the front, or some space is gonna be the 1 meter. So we have to test this very quickly and not turning off the GPS, then to get an error, a formula for the error, to calculate the error, and we get an average and try to do it.
You should cut my yard. Cannot stay in the cutting because
Because we already have the entire when we were testing it, we had to go there. Yeah, we cut it first. In conclusion, we went with the smart, the cost-effective components, and we complete our objectives. That was to develop this autonomous mower, and as well we can assist facilitate this task of mowing.
We can bring it manually, controlling it with the phone if you want.
Okay, well, during the pizza time, you can show some video. You can demonstrate that. Question for them.
what is the final cost? What is the final cost of that?
Exactly was $444. So in the market, they cost around 1,500. So really,
Does that cost include the buying that lawnmower?
yes.
What did you guys think of the hardest part of
The programming,
programming?
yes. Because with the GPS, we had to do the algorithm to reduce the percent error. So that was probably the hardest.
Basically, we have the logic, but we have some logic, of course, gonna be off exploding out. So we have to place that logic on the code. So that was kind of the hardest.
What is the initial information you need to tell the machine?
You have to place the machine on the four corners and
Four. Can you cut any random shape now, or just a square?
just a square.
Hi everyone, my name is Marco Orozco. My advisor for my senior project is Dr. Yan. And I did Wavewinder, which is renewable energy that takes energy from the waves. It's my Gantt chart. It's an overview of what I did this whole year. I did some research on wave technology to compare it to the technology that we have now in the market. Model analysis of what I'm going to design. The materials that I have to use to avoid corrosion, or what will be better for the structure, supporting materials, structure design, using a CAD software, Wavetech analysis for the semester, machining of the parts that I'll be needing, 3D printing if needed, assembling, testing results. What is the Wavewinder? A Wavewinder, it's a wave energy technology that was developed in the UK. Unfortunately, the company that was doing it just turned down the website, so we keep on track with the design. It's technology that has harvest energy from waves. It's a turbo turbine that have a twin helix internal chambers that work in a pumping effect. It's open on both sides, so when it's placed on water, when it's floating on water, water comes in and air comes in on both sides. When it's above the water, it comes in there, and the pumping effects pushing the air through the other side. It's that will make it turn. That's the theory of what they did. This is how it works that I mentioned. They're trapped. It's trapped there because of the two ends are open. The Wavewinder relies on buoyancy rather than drag. So it's more like floating and staying there, trying to tilt it around when the wave hits it, instead of waiting the wave to drag it and turn it around. This is the design. Here you can see how water comes in and air is trapped there, going from one side to another. Where can we put this technology? Well, it's a nearshore device. If everybody here took renewable energy with Dr. Yan, now that we have offshore and onshore devices, this one is nearshore device, and it only needs to be positioned 20 meters depth of what, 20 meters depth of water. So we can have it real near to the shoreline, so we can do maintenance and wiring or everything that we need to work with. Territories with which wave resort will be the better to put this technology to work. Where do we have these territories? In Western Europe, USA, Africa, and Australia. Here I have a map with power in kilowatts per meter of the wave crest width. Here we can see the density. The better place to put it is down there in Australia. And we can use the west coast here in USA or there in the UK. The design, let me go back real quick here. The design here, it's a repeating segment. It's probably the same segment, repeated, assembled together to have the whole structure of the wave turbine. So what I did, I started to did my CAD designs. I started with the repeating segment, but I wasn't able to print it as a whole thing that I designed after. I wanted to print it as a one whole part, but I couldn't because of the 3D printer. It's not available. Well, the space on the 3D printer, it's not giving me a chance to put everything because this one is 1 foot long. So the maximum height that I have is 6 inches. So I cut it in 3 parts. Well, these are the supporting structure and the shaft. The blueprints that I have, the drawings, the shaft, the angle plate that I'm gonna put there, support, and the plate that is gonna be holding the shaft. Here's the Wavewinder Assembly. We can see that I left many holes here to play with the water height and depending on the height of the waves. Up here we have the plates that are going to be connected on a beam that is going to be holding together. This right here is the real model. That one up there on your left outside is the repeating segment that I print. It's 1.4 inches in height. I printed 3 of those and I put it together. That's the assembly of the Wavewinder structure. Here we can see the shaft, the plate, the angle plate, and the beam holding it together. We have in the middle of it the Wavewinder structure. As I mentioned, it has to be floating on the water, and that's the level that we got that is touching the water when the water is not moving. Testing and results. What happens is it didn't work as desired. It only turned a little bit this side and then goes back and forth and keeps oscillating. So Dr. Gantt told me to forget about it. It was a prototype that they didn't put to testing in the real world. We did a prototype, it didn't work as desired, but we came up with a solution. Put it in a vertical way. So here I'm using Miguel's structure to support it and his shaft. I borrowed it from him and I put it this way. And now what I had to do was to wait the water to come hit it. And when water comes in here, it pushes the structure to one side and starts rotating. Let me show you. Here you can see what goes to one side to another, but then goes back a little bit. I don't know what happened. Well, it tried to go all the way around, but then it stops and goes back and forth, keeping on oscillating. So I measured how many times it rotates or give a complete turn. I put it into an Excel sheet. I calculate the degrees, and I correct the degrees because when you have a complete turn, you have to add the, you're not just going 360 and then go back to 1, so 360 plus that turn. I corrected it, and then I wrote the turns through radians per second to get the angular velocity, and this is what I have. I got the angular velocity. You can see here, when it's at 0, it's when it stops. When it's a positive number, we know that it's going in the right way. When it's a negative number, it's when it's going back. So that's the result. This is just a zoom-in photo of the results. And then to calculate the angular velocity and the degree of movement, I put the video in slow motion, and then I broke it down. Into 1,800 frames per second images. So I had 1,800 images, and I just measured each degree, and this is what I got: the angular velocity, and the horizontal axis is like frame rate. That's my results. Do you have any questions? David.
Another question. The very first design, the very first one.
Okay, this one.
That operates on air pressure, you said?
Well, it's supposed to, yeah, to be pumping the air from one side to another when water comes in and it's rotating. It's supposed to do that.
Testing that?
No, because this design that I have here,
It's only half.
it's too small. So water comes in and it barely comes out. So it's full of water, makes it weight more, and probably because of that and the friction with the shaft, it didn't turn well. So that's one of the reasons. Quentin.
I noticed that when you were testing it, and then you covered one on both sides.
Yeah.
Well, one side, and then you made a small hole that you reduced the area where the air was coming out, so it increased the.
It didn't work better than when it's open completely.
But it seemed like it wanted it to turn a little bit faster.
It
so
turned
you didn't
very
have a longer
similar to the
piece.
other one.
Yeah.
It turned very similar. If you seal one side,
Because it increased the air pressure. I noticed that.
yeah, but not at all. It worked better when it's open all the way than when you have small hole.
Basically, for this design, the original inventor, did some simulation using CFD model, and they claim that it works. So I'm curious. That's why Mark is doing this, validating that. But turns out either our current model design may have some problems, or maybe in concept that design never work.
Because it's probably not holding enough air. That's what he's saying.
Yeah,
Yeah,
it's because
it
it's
might
too
be a
short.
reason,
If we do it long enough, probably trapping air and water at the same time, it probably work as the inventor did. So, any other questions?
You said it's no longer the page is no longer up. Is it that it was? You said that the websites that have
Website? No, it's no longer available.
Is it because they just took it down, or because
They
the company?
probably didn't get an investor or something, and they just
Most likely, they
Yeah.
stopped this. They stopped this effort. Seems that they realized that it's not going to work. And there is online. I did see a video showing their testing results. They did it in the wheel tank, but it's working really, really poorly. It's hardly rotating. Yeah. So they have done some testing themselves.
Okay.
It's going to be our.
Good night, everybody. My name is Quentin Garza. I'm a mechanical engineer, and our project is the Ride Control Assisted Robot for the R car. I was in charge of the design and manufacturing.
Adrian Luna, I'm an electrical engineer. I was pretty much in charge of the gun maneuvering, make it move right, and firing it.
I'm Ruben Alves. I'm in electrical engineering, and my main task was to make the tank move and the battery.
I'm a computer engineer, Alvaro Vasquez. My whole thing was to program the movement of the car.
Pedro Fernandez, the computer engineer, and I was also in charge of the gun maneuvering and cameras and wireless.
The whole concept of our project is around keeping the peace. And like last year and this year, there was a lot of incidents between police officers, and there still is, and civilians, where there's misunderstandings where civilians are too close to police officers, and within a split second, an officer might react and shoot somebody. So what we're trying to do is reduce the need for lethal force and make everything non-lethal. So this isn't something to use to attack, it's something to, save lives for police officers and civilians. The main purpose the concept for our robot was, as you guys seen, there's a lot of EOD robots, there's a lot of drones that they use that already have machine guns attached to them and everything. But these mostly are controlled with video feed, and they'll have crosshairs, and you need to remotely move the crosshairs and position them before you actually shoot. So what we were trying to do different this time was to build an actual robot where we could have the precision, and we could limit the time that it would take to aim on a target, and have our video feed on a tablet mobile device that wherever you would put your finger on the screen, you would have the gun automatically log on to that target. Wherever you click is where you shoot. So obviously we don't have the resources to attach a laser rangefinder to give us a distance. That way we could fix the elevation. So we were gonna simulate inputting distances, and that would fix our elevation. And then we would just control on the X and Y direction with our fingertips touching on the screens. Obviously, these are some of the things we kept in mind. We wanted to keep authorities and civilians at a safe distance, so we were creating a buffer, and we needed to create a robot that was going to be rugged, and it was going to be able to sustain damage, and it was going to be able to maneuver obstacles. So we need something to be easy to control, somebody that wouldn't have to take various classes. You could just pick it up like a video game and be able to use it. And overall, it has to be cost effective, because if you do any research on anything, any EOD robots, I'm talking about robots that actually have a lot of technology input into them, but they're disposed of very quick. They get blown up or they get whatever. And they cost upwards to like $100,000 or more. All right, this is the design that we started with last semester, and we pretty much kept it the same, and we made some minor changes that we went on, because as you guys know, that with the changes, the schools and everything, you know, we weren't able to receive our parts on time, so there was a lot of improvisation on our team, fix problems that were coming up as quickly and as cheaply as we could, because most of us put our own money into it. The first thing that I did as a mechanical is that we had to build this frame, and I had the help of the two electrical engineers, because they were also in charge of the manufacturing. None of us had ever welded or touched a rod to the metal before, so I think for the first time we did pretty good. We used a 2.5-inch by an 1/8 of an inch thick angle iron, and that's what we welded to create the frame. Next, we had to do the traversing system, which consisted of 2 bearings, a threaded rod, a nut, and then we're going to mount the motors on the side, and that was going to give us our movement in the X and Y direction. And that system was going to be sitting on top of another of a base, which was going to be attached initially to a rack and pinion, and that was going to give us our Z-axis. It was going to change the elevation. So this is part in the front of to give us more precision, we were going to make the muzzle of the paintball gun be stationary. That way, the only thing we were changing was the back angle and the elevation. That way we knew that we were going to be shooting true. So for that, I needed to make sure that I had freedom in the front of the muzzle, because there was going to be play when it was moving. So I had to move in the Z direction, and I also had to rotate in the Y direction. So this is what I came up with. This is what our base, our traversing base ended up looking like. And if you can see here on the bottom, there is a plate, but it actually, because of the weight, it flips down. And that's what I designed to hold the muzzle of the gun. And that's what the finished part looks like. You see it looks exactly the same. And this is this is what we did change. Here, instead of having a regular bracket holding it, we made another base that would also incorporate the firing mechanism. And then, obviously, we didn't have enough time to find max effective ranges, because we couldn't do any calibrations. We ran out of time because I wasn't able to finish the project ahead of time, because I had to wait on parts. And so that's the only reason we weren't able to find how far we were going to shoot, because our weapon has a max effective range of 15 yards, yeah. No, 15 feet. And then another change that we did to the design was for our elevation system. Instead of I was going to use a rack and pinion system, because obviously you know that's what they use on CNC machines, things like that. That it's more precision. But since I didn't have time to buy it, and it was going to be pretty expensive to come out of pocket, I ended up using a motorized scissor jack, which after brainstorming for a little while, me and David came up with that idea, and actually came out perfect. And then the next thing we also built were the tracks. That's what, when I designed it, at first I was going to use bicycle tires, rubber from the bicycle tires, and 1/2 inch C-channel to bind the tracks. But instead, I ended up using serpentine belts because they were a lot stronger from trucks. I took them off, and then that's what here is my driving wheels that we're gonna use to keep the tracks in place. Those were supposed to be 3D printed. Unfortunately, they were too big for the printers, and then going back and forth to Edinburgh was gonna be kind of hard, so we decided that we were gonna make them out of wood. So, I mean, there's error there, we used a jigsaw, we did it by hand. But this is what our tracks ended up looking like. You can see them there mounted onto the frame and the wheels. Oh, and here on the bottom, I made sure I use skateboard wheels. They're cruising skateboard wheels. I use them as to create tension and to help support the frame. Because the total weight of our robot came out to be weighed with all the components on it, 87 pounds. So those were all the mechanical parts I did, and to maximize the design for whoever takes it next, I think they should first of all upgrade the driving motors and the traversing motors to increase the speed and the way that the gun is going to traverse in the X and Y, because it still moves pretty good, but it should move faster. So also, obviously, the 3D wheels need to be 3D printed versus having wooden wheels, not just because of fire hazard. Or we want them to be precise. That way the tracks won't fall off. Also, the springs that I used were Home Depot springs, which each of them is rated for 90 pounds, which is way too much, but that's the cheapest I could find. So if we had some smaller springs, we could reduce the tension in the tracks, because that was one of the problems that I encountered. There was too much tension on the track, so it kept throwing my tracks off to one side and the track would pop off. So we had to play around with the position of the skateboard wheels. That way we could keep the track in place. And then any wooden parts that we have, like the gun mount and anything like that, they should use high strength thermoplastic polymers. That way, because they're a lot stronger than using regular aluminum, and they're a lot lighter to reduce the weight of the robot. And also the frame should be encased in like thin sheet metal, and we should have all the electrical components and everything inside. And also we need to include a cooling system. That way we make sure that none of the electrical components overheat, because it is going to get pretty hot, and especially if you're using it continuously. And for my expense report, this is everything that I bought, but since we couldn't order all these parts, it didn't have to come directly from my pocket. They could have ordered it too, but I just went $2 over my budget from last semester. But our overall budget, what we spent overall was only $1,030. So we were still $470 under budget. So, and my Gantt chart, the only thing I wasn't able to complete was the calibration of the guns, and I mean obviously because of time constraint.
Okay, so my main task was to make the robot move. For these, first we had to estimate the weight of the robot. At the beginning, we estimated it was going to be like around 50 pounds, so it came out like 87 pounds. So I decided to use windshield wiper motors. They're 12 volts. They come with the gear integrated, since we needed a torque instead of velocity. So these motors, they provide around 29 newtons of torque, and they work at around 15 amps each motor. We're using two of them, one for each wheel. They're easy to install, and they work with the Arduino software, and we just need a motor drive to control the speed and the forward and back direction. For the mounting, after the frame was ready, we just welded another piece of metal so we can mount the motor right. It's actually in a horizontal way, not like that. We just needed to make a shaft, because we needed 3 extra inches so we could make the wheel turns. Well, my friend here already said we used wood gears mounted on the motors, and we just made adjustments so the wheel was straight. For the power source, that was another task. We choose to use only one battery, so we didn't have to charge several batteries at the same time or whatever. We have lighter weight, only one battery, and it's 12 volt, 17 amp. So you can run the robot like around an hour and a half. The wiring is pretty straightforward. We just use heavy duty servo wire. It's a number 22 gauge. It's cheap, it's easy to work with, and the terminals, they came with the Arduino boards. I only spent $106.90 on the, I actually bought 3 motors. I only use 2 windshield motors, and one of them, I use them for to control the gun to the left and right. I also helped on the frame to make the tracks, and to the firing mechanism. We mounted on the side of the gun so we could press the trigger of the gun. This is my initial and my final Gantt chart. The only thing I changed, it was on the research at the beginning to choose the right kind of motors, and the rest is pretty still the same. The testing and everything.
My contribution to the project was, well, I had to move the motors. And to move the motors, I had to do it with wireless communication with the device, being the device, my laptop. And I also had to write a program to move the motors forward, back, left, and right. So I was thinking, well, what software am I going to use? And one of my friends, he graduated last semester, again, said, well, there's Arduino. And I was like, well, let me look into that. So I decided to use Arduino because it uses C++, which I'm really familiar with. And so I looked at tutorials, examples, just to learn the software, see what it can do. And people have done incredible things with Arduino. 3D printers, quadcopters, almost anything you can think of. So the first 2 things I bought was the Arduino Uno and the Arduino Motor Shield. And the Arduino Uno, it basically makes my code come to life. And the motor shield protects my Arduino from using too much voltage that it won't be able to take. And also moves the DC motors, 2 DC motors and 1 stepper motor. So I decided, all right, I have the parts, now let me write a code. So I decided to write a simple code that would just move a prototype forward, back, left, right, without me controlling it, just the program running it by itself. So I built a little prototype, I tested it, everything went all right, it moved the way I wanted to move. So I was like, all right, my prototype works, but now, how do I make it work wirelessly? You know? So I decided to look up on the internet, see what was simple and cheap. And I found the XP. So I decided to use the XP because it was pretty simple to use. We have 400 feet at range. So I had to go back and like, all right, well, I have 1 code. Now I need a second code. So I used my first code as a stepping stone to start with this new code. And I also figured out that I had to use a different program for the XPs in order to configure them, which was the XCTU. So once I did that, I got the parts kind of late in the semester, but luckily I got them. So I got 2 XPs, one to be connected to my computer, another to be connected to the Arduino. And then I got an XP Explorer, which connects to the XP, to the computer, so I can configure them. And I also got an Arduino wireless shield, which will go on the Arduino. After all that, we found out the motor shield I bought originally would not be able to power these motors we were using. So we decided to buy a new motor shield, Polu Dual, and we tested it and it works. It was giving us, these motors are 6 amps per channel. and these gave 12 per channel. So I tested it. I tested the program with my components, and like with anything, nothing goes right. My XP, we're not communicating with each other. The motor shield was not moving the motors. We didn't know what was going on. But after a while, banging my head on the wall, I figured out what the problem was. We figured out that the power sources here are giving enough current. But once we used Ruben's car battery, we started moving the motors perfectly. So after that, after I wrote my code, the components were ready to go. So my code basically will move the motors forward, back, left, and right, all through wireless, through my computer. So I don't have to be connected to the robot or nothing. So we assembled it, right? And again, when you test, nothing goes right. For some reason, every time I go forward, the machine would go left. I go back, it would go right. I'll go left, forward, right, back. So I go back into the program, switch the commands to get everything correctly. And I also came into a bug. For some reason, every time I would go forward, and it would continuously just go, it would all of a sudden stop and then turn right. After I went back to my code and looked through it, it didn't give us that problem anymore. After my Gantt chart, the first semester, my Gantt chart, as you can see, at the beginning it was kind of hard to start. But as time went by, it got a lot simpler at the ball rolling. This semester, well, it wasn't as kind to us as I would like to. I started out fine, perfect. Then you hit one road bump, you get past it, you get another one, So you're stuck or you're behind. But luckily I got everything to work. As for the money I spent, the main project is the money that the school gave me, which I spent, only $218. And the prototype cost is the money I used, because I want to build this prototype and keep it for myself. And in total, I spent $319, which is a little higher than the money they gave us, but only by $20, which is nothing.
So for me, I'm in charge of the paintball event for the marker maneuvering. First semester, it was just doing my research on the different motors. I did brushless, servo, stepper, also the power source, because we weren't sure we were going to use the same one or we're going to use two different batteries or power source. I also reached some drivers to help communicate with the Arduino and the motors. And all the components that were used were the voltage converter. It was from 12 volts to 5 volts, relays, and then the push-pull electromagnetic circuit. For the stepper motor, this is, since our project, our first design, it was going to be, like he said, I chose a stepper because it was supposed to, the holding torque. Right. Yeah, we're gonna use the rack and pinion. So these were my choice. The 12 volts, it was 1.7 amps. Since it was gonna be used for both the rack and pinion and the movement when we first started, but then, let's say it happens, it changed. For the C-axis, we said we use the electric scissor jack. It can lift it to 2 tons, so we don't have to worry about that because when you see it right now, it's pretty heavy. The battery, same as his. It's 11 pounds, 12 volts. And you already saw that, but here's the motor. So it's pretty much just sending the signal. It just pretty much moves. This nut right here, it's gonna go like that, but it stays in place. Well, it doesn't stay in place. This is always just fixed. This will just move the gun. It'll move it on the x-axis. So I use the plywood because it's not that heavy and it's cheap. It's right there, easily accessed. I mean, a lot of the stuff we got here, we just kind of, machine shop. For the fire mechanism, it's the solenoid and a 2-channel relay connected to the Arduino. It pretty much just charges and gives a little push. It's about 9.9 pounds of force. This is my it's a little messy, but it's right here. Here's your Arduino, our step-down converter, the relays, our 2 big easy drivers. Those we can change the current. Since the motor was 1.7, that one goes up all the way to 2. Like I said, it looks a little messy. We use another relay for the jack because the jack was sort of like 2 weeks ago. It kind of improv, but we're trying to figure that one out. I also helped out with the manufacturing of the frame. Well, pretty much all the manufacturing, like I said, it was done by all the electrics, the electronics, or electric and mechanical. The scissor jack mount, I don't have a picture, but I don't know, you'll see it right now. And the microcontroller and the driver mount, which is the one I showed you before. The budget plan, so this was what I spent on. Mine came out pretty, it's $249, but it's because the gun, the tank, that was like about $100. Just in the gun, the CO2 tank, the remote, because we can't really have the tank attached directly to the gun. It gives us too much weight. So for the motors, it was $44 each. It's the 2. Well, like I said, total cost. In our Gantt chart, this was the original Gantt chart. It almost stayed the same, but some things did change, especially the cosmetic upgrades. There was no time for cosmetic upgrades. It was gonna be chrome, looking all fly. Just kidding. But it's pretty much stayed the same, except for, we're gonna make it look nicer, make it look presentable. And the trials, well, since we didn't, the stars, we pretty much tried it till this week, because a lot of the parts that it sent us back for the parts that we had ordered a month and a half went by.
Okay, I'm gonna try to make it short and sweet. My presentation is usually simple. I like to break it down so anybody can understand, even me when I'm not even paying attention to my own stuff. I broke down my portion to 2 very simple categories, communication and maneuvering. On the communication part, we found it very vital that we needed to have it communicate remotely. So we had a lot of options to look at Wi-Fi, Bluetooth. Obviously wire was an option, but wireless, that wasn't an option. And we also wanted to have it compatible with almost anything. As I mentioned there, computers and phones or any kind of other handheld device. It was very important for us to do that. And unfortunately, we didn't get to do the programming for touchscreen, but we still made it work for computers, which can be used on any computer too. So we have the compatibility. And also very important is the feedback. We want to make sure that whatever the tank sees, we can see that right away. We give it a command, it responds quickly, because we don't want to do something and the person is 5 miles away by the time we react to it. That's it. As far as what we see, we want to make sure that what the tank sees, we can see while controlling it on our computers or whatever device we're using. So we were thinking about doing 2 cameras, one on the gun and one on the tank itself, because we're going to be controlling both objects, the tank and the gun, by 2 different operators. So we want to have both a backup device in case one of the cameras goes out, or at the same time having 2 opinions going into a decision, to have a little more control what they're doing. Like I said, it allows for dual view and dual control. And of course, with cameras, we can go Wi-Fi, and that will give us a long range. So the device can be 50 feet away from you, and it still can communicate with the laptop that you're using to control it. And what it does, or does, we want to make sure we input all the commands remotely. Whenever we control it, we want to make sure we're away from it. Again, the feedback must be accurate and quick, and the power to the gun must be able to support any workload that we're setting it. So these are some of the examples of options we're looking at. That's Arduino Uno, and again, we made decisions later on to change that and upgrade that. And a simple breakdown of the communication. These are right here. There you go. Right here we have the interface that we're using. It's very simple put, up, down, left, right. The triggering mechanism is right in the middle, so you just hit fire. We have two different controls. One of them, if we wanted to upgrade to have only one device, it was in there so we could control the tank. And on the right, you have to control the camera and the gun. I'm sorry, not the gun, but not the camera, but the gun. All of these devices are all connected by the router. The Arduino has a Wi-Fi shield. The camera is Wi-Fi integrated. It could either be through IP or connect Wi-Fi through the router. So it could go directly to the laptop or communicates through the routers as well. And what was that? That's on the communication as far as wireless. You have the camera, like I mentioned, the laptop, and of course the Wi-Fi shield all communicating through the router. And then the center hub for what we're using, we used Python GUI, which a couple of people said. He created an interface that is very simple, like I showed right here. So that way you can go and just give the commands and it responds directly. And the step that it goes through is you go through the Python GUI, then it breaks down to the Arduino, which then sends information to the motor drivers or to separate motors or whatever else we have connected to it. As far as the maneuvering, we had the stepper motor being used right here. It's a stepper motor actually on the other side, but it's being used here on the threaded rod to move it on the horizontal axis. The electronic scissor jack, which you can also see right under here, was used to move it along the vertical axis. And we used the solenoid pin to hit the trigger right there, using the electromagnet pretty much. And of course, right here in the picture, we have a motor driver. I also saved this at the last minute, providing that because the one we had actually didn't work for it. So we had that motor driver helping us out to connect the jack to the Arduino. Quick sample code of from our Arduino interface. Here is just listening to the commands from the GUI. Every time it inputs, you press the up button, it sends a command to it, which then it converts and switches back up to the whatever device you're trying to control at that point, I guess. Again, the interface, this is it right here, up, down, left, right. We weren't utilizing this because we wanted to have separate controls, but again, like I mentioned, we can always go and put that in there and have it controlled by one and the firing mechanism. Right here we have a laser set up right in the center, and this is what the camera is viewing right on the tank. Quick overview of my budget plan. Spent just under $200. We could have spent a little more, but we didn't expect it to get here in time, so we stuck with what we had. First look at my Gantt chart from spring 2015. There was a lot of modification. Obviously now, looking back, there's a lot that I did not know, and that's what a lot of the modification was. I thought I knew more, so my plan was that, and then changed a little bit towards the end. And the last semester Gantt chart, I was pretty much on pace towards the end. That's when we fell back, but we moved along there. And I think that's it. Yeah. Yeah, that's it.
All right, this is how it started looking when it was starting to get built. And it's here without any of the components, and then we're going to lift that so that we can see what it actually looks like. We're going to make it all.
It's not like
But I mean, I think it looks pretty good for. We didn't get it to where we wanted to, but we left it in a good place for somebody for the whoever takes it up next to take it to where it's supposed to be. So most of that is gonna be programming and, you know, connecting the cameras to your program and being able to actually, what is it? I don't know the word. Well, well, you get what I'm saying. This video here is showing where they're controlling it with the computer. You can't really hear it, but it's firing. And obviously, like I said, it would be better if we upgraded the motors. That way, it can have a little bit. It'll be a little bit quicker. But on this video, you'll be able to see a better video of it doing the job. Alright, you hear that? That's the firing, and that's the alarm going off in the machine shop. But that's pretty much it. Any questions?
Are you using two computers? You're using two computers to control it?
Yeah, we're using two computers. Obviously, it's going to be pretty hard for you to. The whole point is to have two people on one robot. You don't want the same person to be maneuvering the robot at the same time because you can't react as quick when somebody flashes by in
You
front of
have
you.
two different microcontrollers for doing different things.
Yes. Question?
So how fast can you shoot?
As fast as you can click.
No, but
Oh, la velocidad.
the trigger that you have.
Yeah, it's only
you can
you can
It's got like a second.
yeah.
So like what's the second?
Probably. No, I think it's probably quicker.
Yeah. I mean, you
That's
can't,
probably
it's
quicker
not
than
gonna
that.
be unless you want it like a automatic machine gun then.
Probably.
See the damage.
It's because it's really sensitive. The trigger is super sensitive. So I mean, we could try to.
Have you tested
I don't know if we have.
have you tested the range and
We were able. We shot it at 25 and
Accuracy.
50. At 50, yeah. And it was 50 feet.
do you have any data?
We have some videos, but we don't put them on here because they were kind of hard to see.
Better show some data. I mean, with the limited range, you put a target over there. You know how
Yeah,
to show the data.
that's what I said. We weren't able to because of the time constraint. Because I wasn't able to build it in time because the parts. Actually I ordered the parts and it took 6 weeks.
Time shouldn't be constrained. Everybody share the same 2 semesters.
Well, not 6 weeks for them to tell me no. Because I ordered my parts and it took them a month and a half to reject my order. And then I had to order my parts again. Because if I would have bought them at the same time.
I know many people are complaining about the purchase in this semester. Remember one day you become the manager of project, you are the one that is responsible for everything happen, right? Just